So recalling from the problem last time I discussed on the homework 5, actually homework for problem 5b on the p and plus 1 and plus 1 plus 2, I believe. And p and 0 is 1 plus 2. So what did I show? I showed 0 is no recurrent, and I did step number 1. 0 is indeed recurrent. Right. Of course, let me mention here. Positive recurrent means that returning time will be finite on average, and no recurrent means I may wait forever to return. So 0 is recurrent. That was because the probability of starting from 0, t0 being infinite, is the limit of probability t0 is greater than n as n goes to infinity, and we show this event here is valued from above by 1 over n, and so taking the limit back going down to 0. Is exactly right. So that is the first step. We established this recurrent property. So now the next step is to show step 2. 0 is no recurrent. In other words, I need to prove starting from 0. I wait forever in order to go back on average. And well, so this is actually pretty, I would say, a consequence of this identity. A consequence of this identity that we proved the last time. So we recall expected value of a discrete random variable taking values in the integers is simply the probability summation of starting from 0. t0 is greater than n for n starting from 1 to infinity. And well, so now all I have to do is just to plug in the this identity. So I guess I can do here is just a summation of 1 over n starting from 1 up to infinity. What is the value of that series? Infinite. Infinite. It's a p series, right? P series where p is 1. So this is infinite. Yeah, pretty handy. Yeah. All right. Yeah.
The limit p0 t0 greater than n is equal to 1 over n plus 1.
I mean, the limit here is 0 because I take n to infinity. So if if you look at the homework, the fact is, so not here. Indeed, what did I say? There exists a stationary distribution on S. Alright, so this is the content of the problem 5b. Okay. Once we have this property in the following theorem, then pretty much everything follows correctly. So, theorem number 2. Suppose S is irreducible. Alright, then the following hold. So actually the followings are equivalent, as we say, equivalent, not whole. Equivalent. Part 1, there exists a positive recurrent state. This is equivalent to there must exist a stationary distribution pi, and all equivalent to all states are positive recurrent. So if one state is recurrent, if one state is positive recurrent, that does imply existence of a stationary distribution pi, and that does imply all states are positive recurrent. Of course, provided the state space S is irreducible. Alright, so 1, 2, and 3 are equivalent. For the proof of this, I will just refer to the textbook. Alright, see textbook. It's pretty short. Okay. So as you can see now in this homework problem, this state space here is irreducible. Everyone communicates with everyone. But then, I already have one guy being no recurrent. And so actually the truth is, what? I wouldn't have a stationary distribution pi. So actually this is the following corollary, which is a consequence of this theorem. So corollary 3. Again, I suppose I still have the same. Suppose I still have the same irreducibility. S is irreducible. Right. Then all states are either one of the following. Either or everyone is transient, either they all are transient, or they are, every one of them is no recurrent, or last case, positive recurrent. So if one guy is transient, the rest has to be transient. Or if one guy is no recurrent, the rest must be no recurrent. And similarly for positive recurrent. So pretty quickly, I would say the argument is pretty straightforward. I would say pretty short. Yeah. So suppose all states. I would say if all states are transient phenomena, then right. Now if suppose I have one guy being recurrent, then by irreducibility, everyone must be recurrent. Okay. So now if one state is recurrent, then by irreducibility, all states are recurrent. Right. So now suppose, so now keep going. If all states are, so I guess this is further. If all states are no recurrent, then I'm done. But now if only if I say, let's say I have if one state is further positive recurrent, then by the theorem 2, all are pretty short argument using that theorem 2. I believe this is the theorem 1.29 in the this is theorem 1.29 in the textbook. Okay. So at least that is something you can say when you have when you have the irreducibility, you can classify all the states, and if you don't have irreducibility, then pretty much it's a case-by-case basis. It's a hard problem in general if I don't have irreducibility. Is there any question? So that should be it for the theory of chapter 1. Right. That should be it. And you should be able to take a midterm now. Now let me walk through the practice. Okay. So this is problem here is about a very famous model in population, the so-called branching processes. And what is the idea? So basically, the idea here is kind of just model the birth and death of a population as following. So suppose I have one individual at the beginning. Then we're going to say, okay, this individual will give birth, all right? Give birth to, let's say, a number of kids, all right? Let's say, K kid from the parent, right? And this individual will give birth to K kids with the probability denoted by let's say one is the number of kids. So, alright. And so and so suppose, and then so each of the kids here independently will give birth to the next generation and keep going, so, and keep going. The question is, suppose I start the population with only one person at the beginning. What is the probability they will go extinct? That is the ultimate goal of the model, is to evaluate probabilities that the society here will go extinct, given that at the beginning only one person. Right? So that is the ultimate goal. And so now here in this practice, we pretty much formulate a Markov chain on the number of the number of the individuals in the nth generation. So let me denote by x and tb, sorry, I guess I want to say population, I guess. Population in the nth generation. Right? And suppose here at the nth generation, I have say I have k numbers, should call k, what do I want to call, maybe call it n. So I have let's say I have, this is number 1. This is, right, suppose I have n individual at the nth generation. Every one of them independently will give birth, right? So here in the n plus 1 generation, so here I have x, and is mean n, it's going to give birth here. And so this person will give birth to a y1 number of kids. This person will give birth to a yn number of kids. So you take a sum every one of them, that will be your x sub n plus 1. So hence, x sub n plus 1 is simply the sum of the y. So yi from 1 to so that tells you what is the transition matrix. So now that can tell you that the transition matrix is given by transition matrix given by, so the probability of so let's say x1 being let's say m, sorry, what do you want to call being, let's say k, given x0 is m, alright, or p and k, so p and k is equal to this. This is basically the probability of the y1 plus y0 plus ym in k, where the yi or iid with that PMF function. So where yi or iid Sorry?
Like right under the y
Where the yi or iid
I. Oh, okay. Or IIG with?
with the PMF, the mass function.
Oh, okay, okay.
Yeah. Discrete situation. Okay. They are IID with this probability mass function. Right. Okay, so the ultimate question, as I just mentioned, so the ultimate question is, suppose I start the population with only one individual, what is the probability they go extinct? Okay, that is the ultimate problem. So to prepare for the asymptotic behavior, let me walk through the first problem. So what is the first problem? What is the first problem? Of course, here we have to assume that if I don't have any population, then I cannot have any kid. So of course here, I guess I forget that piece. Of course, we assume, P00 here is equal. Because if I don't have anyone, then I cannot give birth. So the matrix goes like this. So 0, 1, 2, 3. 0 will stay at 0 forever, probably 1. You can think of 0 being a absorbing state, right? And 1 could go to 0, 2 go, and so they could go anywhere, basically. And what else? That, maybe, and whatever. Okay. The only foreign piece here is if I if I start at 0, then I'm going to stay there forever. That's the only really important piece. All right, now suppose the person does not have any kid with that probability P0 positive, right? Or probability the person will give birth to one kid is less than 1. All right, so you look at the parentheses here. Then every state starting at 1 must be transient. So the first part is pretty, the first condition is pretty, so suppose I have P10, right? And this is probability start, assuming I have only one individual, probability the individual does not have any kid. All right, and this is also equal to P0 because this is the probability y1 is 0. So this probability is positive. Then everyone must be transient. The reason because if I start from here, there is a positive chance I go down to 0, I stay there forever, then one has to be transient. Similarly, suppose I have 2 persons at the beginning. Each one of them has a positive chance to give no birth. The 2 could also go down to 0 in one step. But once I'm there, I will stay there forever. And so the 2 must be transient as well. And similarly for 3, 4, and whatever. So how do we say that? Now suppose, let's say for all k, or maybe for all x, starting with 1, okay, I have, what? So the probability of this is less than probability starting from x, tx being infinite, right? Because once I hit 0, I cannot go back to x. And so, what is this though? Okay, so now we're this. I want to show this is positive. Now, the probability if I have an x persons at the beginning, and the next generation I have no kid, is what according to the definition of the transition matrix, that is a probability. That is a probability that I have a y sub 1 plus a dot plus y sub x being 0. So look at that and compare it here. Right? So the sum of the kicks is 0. And that does imply, that is the same as saying everyone has no kick. Everyone has no kick. So that is the same as saying y1 being 0 and y sub x is 0. And now by the independent, that is a product. That probability y1 being 0. So I guess I want to say y1 to x. And that is over here, that is P0 raised to the power x, which is positive. Yeah. So that does imply probability of x, Tx being infinite is positive. In other words, x is transient. On the other hand, I suppose now suppose what p not 1 now instead is less than 1. If p11 is less than 1, right? Of course we will assume that guy is 0. Assuming p 0 is 0, okay? Because if we already have p10 being positive, everyone is transient already. So now we assume this and that, right? So can you? So what is the idea of the think about it, right? So suppose I have a warning, let us say I have a warning individual. Either in the next generation I have to give birth to either one kid or whatever number of kids. And so as you can see, the number of the kids is at least 1, for sure, because this is already 0. So y1 is always greater than 1. And so in order to go back to one, that means the only possible to go back to one person from here, the only possible choice is this. For instance, because the moment I have, let's say, the moment I have, say, 2 kids, let's say I have 2 kids, could I ever go back to one? No, right? Because each of these guys here must give birth to at least 1 kid. Here, at least if they gotta have 1 kid here, so at least I need to have, let's say, 2 grandchildren. And from here, so and so on, right?
Yeah, question.
Yes.
Will you get the P10 equals 0?
Suppose if it is positive. Suppose it is positive. We already proved they are transient. Right? So that's trivial. So now,
Oh, yeah.
yeah, we will assume P100. Right? Yeah. So that will be the idea, right? So how do I explain that? I have, so not here, right? So observe, for all k starting, for all, maybe for all x, starting from 1, right? The probability, right, starting from x. What do I want to say here? So Tx being, let's say Tx being n, okay? So what do you want to say? So Tx being n, that is the same, let's say, starting from x, x1 must be x, x2 must be x, and xn must be x. That is the only possible. That is the only, oh, sorry. Well, there's something awkward here. No, that doesn't seem right. It has to be different from x, right?
Yeah.
So, what do you want to say? So, that is something awkward when you come back to this one. You want to prove. So, Tx. Remember the proof here. I guess we're going to do that. Tx is greater than n, then where's my, oh, I forgot. If I can prove that, then I will leave that as an exercise, I guess. And, oh, okay. So what is the claim? So P K. What? Sorry, guys. So I got this piece. So what I really want to say here is the probability of from x giving birth to x kid is probability is P11 raised to the power x. Okay. How is that possible? That's because suppose I have x persons. Suppose I have x persons, right? And then in the next generation, we have exactly x kids forward. that is the same as saying every one of the parents here must give birth to exactly one kid,
Yeah.
right? Every one of them must give birth to exactly one kid. So that goes this. And so that is equal to, so that is equal to, so we know that really, it's a probability of y1 plus y sub x these things. That is the same as probability of y1 being 1. The second person only gives birth to one kid, and x being 1. And so that's a product. So that is p11 raised to the power x. So right? Yeah. Okay. So similarly, so to say similarly, how about p and xx? So I have x persons at the beginning in the nth generation.
This one is kind of
How is it possible? How is this possible? To have exactly x?
you have for example one x
It doesn't rise to the end,
And how is that?
because if you go up one, you can never go down one.
Right. Because if I go up, then it can never get back. And so these are the only possible ways, because in the first step, it goes x, and then in the next step, I just stay at x, and similar for a total n terms. Yeah. And so as a consequence, this is just p11 raised to the power of x, and then raised to the power of n. Alright. So to combine everything, I have a summation of p and xx, and starting from 1 to infinity. That is the summation of n starting from 1 to infinity p xx. So p11. So that would be p11 raised to the power x raised to the power n. And well, this is geometric series, so that is equal to p11 x over 1 minus p11 x. Yeah, geometric series. So this is geometric series. But what is the key word here? So the key is this ratio here is finite. Right, it's finite. So we're calling the result. If that sum is finite, then x must be transient. Finite because obviously we have the condition that p11 is less than 1. This is finite since p11 is assumed to be strictly less than 1. And as a consequence, we know that x must be transient. Okay. So let me recall here. So summation of p and xx. Step first problem. So how about the second one? What is the second one? Alright, so on average, I want to compute the population at an generation. So the idea is pretty much the same as these try to evaluate P excess over here and try so I guess the way to go here is to do a what is the method here? What should we do? Well, I would go with induction. Induction. So the induction here, either you could go with K or you could go with the N. So I would go with the N. I think that would. So I would go with the N here. So we start to have, so suppose I have N being 1. Right. On average, how many kids should I expect to have, suppose if I have a K parent? And so the idea here is now for problem 2, induction. Check this one and read. Okay. So what do I need to show you? So need to show expected value starting from K parents. In the first generation, I have the number of kids on average each K times B. Right? But this is pretty, I would say this is pretty intuitive. This is pretty intuitive because say I have K parents, right? K of them. Each of them give birth to on average to male kids on average, right? This guy gives birth on average to male kids, and the same on this guy. So the sum will have to be K times me.
So can we just, can we just say which is authoritative to this?
Yeah. So okay, let me just finish this. So the probability, so this is the value K is 1 being the summation of K, what is that? So I have so I, probability of X1 being I, given that X0 being K. So that is the summation of I, probability of, this is the same as Y1 plus Y plus YK being I. And that is expected value of the sum of y. So this is the expected value of the summation of y1 plus k, and that is the summation of the y, which is k. stop here, finishing chapter 1 here, and